These two prototype houses were built in New Orleans, Louisiana, for families whose homes were destroyed by Hurricane Katrina. They were designed by Building Science Corporation with support from the U.S. Department of Energy's Building America program. They were built by Catholic Charities, local organization, and LSU Ag Center's LaHouse Resource Center faculty had the privilege to facilitate. I call them the wash and wear houses, a new definition for high-performance housing. What is a wash and wear house, you ask? And why? We all know about the devastation of Hurricanes Katrina and Rita, and the new meaning and focus that this gave. A slogan that we use: as we shape our homes, we truly are shaping our future. The impact of the devastation of these storms on so many families is just beyond words. The work they went through, the time, the cost, the ordeal, and the toll it took on so many people is unspeakable. The impact on just one state was tremendous. Almost a third of the housing stock had been damaged by that storm, along with tremendous public and private costs in many ways. Complicating the losses and the destruction was the difficulties in restoration rebuilding because of the shortages. It was so massive. There were such tremendous shortages of skilled labor, of products, of the availability. Prices went through the roof of many things. It was very volatile. Insurance companies were retreating and costs went up, utility surcharges, the list goes on. So if we ever have another big storm like Katrina or Rita, will history repeat itself? Not if we learn from the lessons and we build resilient housing. For housing to be affordable and resilient, we must consider that climate and conditions really matter and make a difference. This presentation is designed primarily for the southeastern region, warm, humid, and the mixed humid climate zones. Climate zones 2, 3, and to some degree 4. This area, all the coastal states, are also in a high-risk hurricane zone, but no state of the Union is immune from natural hazards. Every state is subject to some type of natural hazard, and high winds is often part of it. For anyone who seeks to create sustainable or affordable housing, durability must come first. If it can't survive the natural hazards of the area, it is neither sustainable nor affordable. Today we will touch upon all of these components of durability and use these houses as examples. First of all, to be a resilient home in possibility of any kind of flood hazard area, we're talking about flood hardy homes. The best way is to elevate the house above the potential flood level. That generally means 2 to 3 feet above the required base flood elevation, because that also has the benefit of giving you the lowest flood insurance premiums. There are several ways to handle raised foundations to be able to do that: pier and beam, stem wall with flood vents, or a slag cap over a filled stem wall foundation. But wherever flood levels are uncertain, or they could go higher than the BFE for whatever reason or in the future, it can be a prudent investment to do what's called wet flood proofing. In other words, to make everything in the area that could be exposed to flood waters resistant to flood damage by elevating equipment, using water resistant materials, perhaps removable wainscoting. We'll see more about that. Here is a concept that really came about after Katrina and for New Orleans. For homes in levee-dependent areas or coastal areas where the flood risk is variable and it depends on infrastructure to be able to stay within the base flood elevation, we propose the concept of the wash and wear house. This shows one way to achieve that, particularly in new construction, with a drainable, dryable wall assembly. Notice from inside to out, on the right side you'll see that the wallboard is made from paperless gypsum wallboard. No paper facing, instead there's fiberglass matting. And there are gaps between the panels. The reason for that is you cover that up with molding, and after a flood you can take off the molding, flush it out, let it drain, let it dry, and go back without having to gut and replace. So to make this wall very drainable and dryable, there is no insulation at all between the studs in those stud cavities. So there's solid wood studs which can survive a flood, then treated plywood, which is more flood resistant than engineered type wood such as OSB, then house wrap, then rigid foam, closed cell rigid foam insulation, all to the outside of this assembly, then some furring strips or something else to create a drainage space to allow good drainage behind siding, and a water resistant siding such as fiber cement. This kind of building system would not need to be gutted, and people would be able to move back into their homes quickly. So those concepts were applied to these prototype homes, which Catholic Charities named them the Green Dream Homes, home number 1 and home number 2, because they were flood hardy, they were wind resistant for hurricanes, but they were also very highly energy efficient, green, and built to be affordable. From ground up, here are some of the components of these prototype homes. They were all elevated to the base flood elevation requirement plus 2 more feet, so that put them about 5 feet above the ground. However, when the levees failed, the floodwaters on these same sites were 8 to 10 feet deep. So if the levees ever fail again, that's not enough. They were on precast concrete piers on grade beams because of the unstable soils. The houses were framed entirely with materials that could withstand flooding. That's solid lumber studs and framing and plywood. No OSB, no laminated strand lumber that can delaminate. Instead of using fibrous insulations, which would have to be replaced after flooding, both homes used closed cell foam type insulations that are flood resistant materials. They don't take in water. The first house used closed cell spray foam in the wall cavities, but just a partial fill, no more than 60% of the depth of the stud cavity, to allow some drainage and drying capacity. The second house used rigid isocyanurate foam board outside of the sheathing, which also and outside of the house wrap to insulate the raised subfloors. One house used fire-rated rigid foam panels underneath the floor joists, completely encapsulating them, taped and sealed with all penetration sealed. The other house used closed cell spray foam between the floor joists and along the rim as well. This creates not only a flood-hardy insulation system, but it also protects the subfloor from moisture problems due to moisture migration. This creates an insulating, airtight vapor barrier subfloor insulation system. On the interior and the exterior, more flood-hardy materials. Inside walls were finished with paperless drywall with a moisture-resistant core. Paperless drywall with fiberglass matting has no food for mold and no food for termites either. And it can withstand even relatively long-term flooding. On the exterior, the fiber cement siding and trim was used on top of furring strips that allow drainage behind them. And solid wood plank flooring and tile flooring was used on the floors because they are restorable. Wood can swell and you may need to pick up planks and release some pressure, but generally the swelling will go back down and they can be refinished and restored. This shows some schematics of the concept, particularly of using the rigid foam board on the outside. So you can see on the left, the rigid foam board is providing the insulation under the subfloor joist and outside of the stud wall framing. Then, after a flood would occur, removing the baseboards and the top molding would allow drainage and ventilation. Removing some of the foam underneath the house would allow drainage there. Then it could simply be taped back into place after everything is dry. Also notice that it's important that the ground under the house be higher than the surrounding ground to allow good drainage as well. The houses were also hurricane hardy or hurricane resistant, wind resistant. For hurricane resistance, what are the major building envelope issues that forensic studies of problems have shown? The number one source of damage is generally loss of the roofing. The roof sheathing comes next, then problems occurring because of broken windows. Broken windows can lead to pressurization, and that can cause structural problems. Window and doors coming off, garage doors collapsing, water leaking, and then of course ridge vents, gable vents, and soffit causing damage as well. So the prototype homes included very hurricane resistant roofings with plywood decking using ring shank nails, which have great holding capacity at 6-inch spacing all around. On top of that, the peel and stick membrane underlayment served as a secondary moisture barrier, very resistant to being blown off by wind. Then the underlayment was topped with wind-rated shingles. Class H wind-rated shingles are tested to 130 or 150 miles per hour. They were also rated for hail, Class 4 hail-resistant shingles. So they would likely be able to survive almost any hurricane that would come along. Of course, they must be properly installed, and in most cases, the manufacturers recommend a dedicated starter strip, not just turning the first course upside down. It has special adhesive, and then 6 nails per shingle is usually what's called for. The windows were not only energy efficient Energy Star windows rated for our particular climate, but they were also impact rated windows, so exterior hurricane shutters would not be required. The windows also have high DP or design pressure ratings. Basically, even if you don't use impact rated windows in a high wind area, you do need to meet the design pressure ratings, and this has to do with the window staying in place with the positive and negative pressures that can occur. Keep in mind that as the size of a window changes, so will its DP rating. And so the larger the window, that tends to lower the DP rating, so it can be more cost effective to use multiple smaller windows to get these higher DP ratings you need, and to also keep windows away from corners. Corner windows would need higher DP ratings. When a hurricane happens, the forces it puts on a house is like turning it upside down and shaking it. That is more like what it's going through. So think about doing that to your house. Where would it come apart? Those are the weak links. And that's what hurricane connections are designed to do. So these houses were reinforced with metal hardware and hurricane connections to resist up to 130 mile per hour wind loads. That means creating a continuous load path that connects all the framing members together from the roof all the way down to the foundation, tying it all together. In addition, continuous sheathing was used, wrapping the house with plywood. This helps to make it rigid to resist the racking or leaning forces by strong winds. And the sheathing was nailed on all edges, so there's framing behind every edge of the sheathing. In addition, hip roofs are more inherently aerodynamic, so more resistant to wind pressures and damage than gable end roofs. And they have the added advantage of providing shade and the energy savings from that, and helping to shed water away from the foundation to prevent moisture problems and help all the exterior materials last longer. Which brings us to the next section of durability, is keeping the materials dry outside of a flood and a hurricane. Because even when we don't have a major natural hazard event, we do have lots of rain in a warm, humid climate. And wet is going to happen, but can it dry? What is key in every home, whether or not you're in a hurricane or flood zone, is assembling everything in a way to keep the wood dry in a wood frame building. You may have heard the mantra. If not, here it is. Drain the rain on the drainage plane. This is so important. A drainage plane are materials outside of the wood that would direct water down and out, that are resistant to rain. These days they're often called weather-resistant barriers. But it needs to start at the bottom with a flashing that'll kick the water out once it drains down. That should be in place first. And then either house wrap or building paper should be layered over that bottom flashing, and any layers of that should be layered shingle fashion. We highly recommend using very tear-resistant materials, and in the Deep South, low perm is helpful. Low permeability types of house wraps or materials are helpful in a hot, humid climate because they reduce the water vapor moisture drive into the wall system. Third step in the drainage plane is to be sure you create a drainage space, a gap between the exterior siding or cladding and the weather-resistant barrier to speed the drainage of water and also to help with the drying of materials. They will last longer. So the prototype houses, the Green Dream 1, had house wrap with furring strips, and then to provide that drainage space, and then the fiber cement siding on top. Now, to help prevent insects from crawling up behind the siding and harboring in that space, the bottom of the furring strips were wrapped with an insect screening. Very simple, inexpensive procedure. With Green Dream 2, all of the insulation was on the outside as rigid foam. So first there was house wrap installed, shingle fashion. Then the rigid foam insulation, which was foil-faced, was placed over that. Furring strips on top of that provide a nail base for the siding and also separates the fiber cement siding from the foil where if they touch, they could react. The weak link with the drainage plane of most walls is the detailing around windows, doors, and penetrations. It is so easy to lose that shingle fashion concept, but it's crucial and important. You know, a complete drainage plane done completely right is really hard to find in the real world, in the field. But it's even harder to go back after a house is finished and add it. So let's take a look at what the steps are to do a really good, robust drainage plane, even around penetrations. First of all, start with cutting out the window opening in a pattern similar to an upside-down martini glass. The wrap is folded in on the sides and the bottom, but at the top, a flap is turned upward, and you'll see why later in just a little bit. Then it's helpful to create sort of a back dam on the sill so that if a window leaks, the water will drain to the outside and not inward. But notice at those corners of the windowsills, when you wrap in the house wrap, the wood there is not protected. That needs special protection. So here is where sill flashing and corner guards must be done properly. There needs to not be only sill flashing, but something protecting those corners. There are many different products on the market now, many wonderful, quick, and easy to install products. This shows just a couple of possibilities, but you can see there's the moisture resistant flashing over the sill and down the face of the wall for a little bit, and then a corner guard that is integrated with the house wrap so that if there is any leakage anywhere, it drains to the outside and does not get the wood wet. The next step is to install the window. Generally, most windows have flanges, and so it's set into place, made level and plumb, of course, but it's set over the sill and the corner flashing system, but under that top flap above the window of the house wrap. In step 6, flashing tape is used along the sides to cover the flanges, and across the top flange under that flap. Then the flap is brought down and the edges of it taped to create shingle fashion there as well. It creates a kind of a head flashing. You can see it being taped down here in these illustrations and folded down. A big flaw that we often see in the field is that contractors might start this process correctly, tape all around, but then they tape that bottom flange. That is a mistake. Do not tape the bottom flange. Many windows eventually leak, and when they do, if you tape that flange, where will that leak go? It cannot escape to the outside, it will go to the inside. So for the best drainage, what's really best is to insert little plastic spacers under that bottom flange to create a gap, a drainage space, so any window leakage can drain to the outside very easily. The air sealing occurs on the inside, the gap between the window frame and the framing. This is done with expanding foam. The type designed for windows and doors, it's a low expansion foam, or with caulk. That also helps to prevent wind-driven water from coming in. But it's an energy saving feature as well. Here you can see on the 2 Green Dream projects the robust flashing systems that were utilized on the 2 houses and the foam sealants on the inside of the windows. Another category of natural hazard is the Formosan subterranean termite. That is the most destructive insect on the planet. They're not like our native termites because the colonies can get so large so fast. They have been known to completely destroy home within only 2 years and cause major structural damage in 1 year. For that reason, we advocate that multiple lines of defense are prudent, wise, and create a sustainable hazard-resistant home. So for that reason, our Green Dreams used integrated pest management rather than just relying on soil treatments, which were used as well. We also had several lines of defense. Precast concrete foundation, raised off the ground with good inspectability and termite shields, but that third line of defense are treated lumbers. We use borate treated lumber, treated plywood, composite siding, and of course good landscape integrated pest management practices and moisture control throughout the building system because termites are attracted to moisture. Another factor of durability is just choosing materials that are designed to last a long time, whether or not you actually have a hurricane or a flood. So going with materials that have a longer warranty are not a guarantee they'll last that long, but they tend to be more durable than materials with a shorter warranty. We used pre-primed fiber cement siding because the paint job will last longer on it and it'll need less painting in the future. Long warranty windows, roofing, and of course it's very important that the foundation be designed for the soil conditions so that you don't end up with foundation failure issues and structural issues resulting from that. And even the equipment and appliances inside were selected for long warranty periods. In addition, pressure treated woods, masonry, Composite components are often very long-lasting and low maintenance as well. Long-lasting floorings, interior finishes, and finally, Energy Star appliances not only save energy every month on the utility bill, but they often tend to be higher quality, which can make them more durable as well. The Green Dream One finished product. Let's take a look at some of the results. It's in a hot, humid climate. It's a 3-bedroom, 2-bath house that's estimated to use about 42% less energy than a brand new code compliant home of the day. Her score was 64. It was designed with an R33 roof with 9¼ inches of open cell, low density spray polyurethane foam under the roof deck, creating an unvented attic. It has R16 in the exterior walls with 2½ inches of closed cell foam there. R13 under the floor with 2 inches of foil-faced ISO board, and of course, low E Energy Star windows. Here are the stats on the windows. What's most important is that SHGC, that stands for Solar Heat Gain Coefficient. The smaller the number, the better, because that indicates how much heat of the radiant heat of the sun will actually get through it. These were fairly affordable vinyl windows, single hung, double pane insulated glass, but they were also impact rated. Green Dream 2 home was built for a very large family of 8 people. It has 4 bedrooms, 2 baths. Its HERS index was 56, indicating that it should use about 57% less energy than a code minimum home. Both of them had reasonable construction budgets within the Road Home Reimbursement Program, a disaster assistance program. The enclosure design included an R30 roof with 7 inches of open cell spray foam under the roof deck, R13 exterior walls created with the 2 inches of foil-faced ISO board sheathing, and R15 under the floor with 2½ inches of closed cell spray foam under that subfloor, and of course low solar heat gain coefficient windows. Here are the stats on the windows, impact rated, insulated glass as well. A big factor in achieving really high performance from an energy standpoint is to eliminate duct losses and losses in that air conditioning system by putting all of the system, including the ductwork, within the conditioned space. In other words, inside the thermal envelope, the boundary of where insulation and air barrier is. Of course, the ductwork is also sealed tight, so it will get to where you want it to be. And we include controlled ventilation. The concept is to build tight, get all that ductwork on the inside. That will eliminate the typical 30% energy loss and moisture and air quality problems associated with it. But build tight, but vent right. All homes need some fresh air to dilute the off-gassing that occurs from just living in and having materials inside a home. But it should be controlled so you don't have too much and you know where it's coming from and it's clean and filtered. Now, when a home is very energy efficient, it can get to a point where you don't need much heating and cooling. That's the whole idea, to make it real energy efficient. Reduce your bills, reduce your heating and cooling loads, but that doesn't reduce the dehumidification load that we have in our warm, humid climate. So supplemental dehumidification was provided so that you can have good indoor air quality and good comfort, whether or not you need any real heating or cooling of the temperature. Where is the ductwork? Well, typically in our part of the country, ductwork is in the attic. We don't have basements, and the attics are normally vented attics, which means the ductwork is in the hottest place on earth, someone's attic in the summertime. And you just think about the logic of that. Doesn't make a whole lot of sense from an energy efficiency or comfort standpoint. It's just a convenient place to put it. So you can eliminate that extreme condition for your ductwork and eliminate those losses by changing the insulation boundary from the ceiling below the ductwork to the roof above it. That is the main purpose of an unvented attic system. And here, that's what was used in these homes where the insulation was at the roof line, and that put the air handling unit and the ductwork within the insulated envelope of the building enclosure. What is the ductwork? By and large, insulated ductboard and insulated flex duct branches. So there was a central trunk and then branches that could have smooth, even curves, but everything was sealed tight with mastic, not with tape. Duct tape does not hold very long, and even the specialized UL approved tapes must be meticulously installed to manufacturer procedures and specifications in order to hold. Controlled ventilation was provided in these homes. Outside air was ducted to the return side of the air handler from an inlet in the wall under the overhang, a clean air location. Outside air then mixes with the indoor air through the air handler and back to the living space. This provides a slight positive pressure in the house, which is ideal for a warm, humid climate. That slight positive pressure then helps to reduce the incidence and prevent hot, humid air from being drawn through the building and into the cavities and possibly resulting in some hidden condensation. The ideal relative humidity indoors for both comfort as well as for health is a relative humidity between 40 and 60%. Even better is below 50% if anyone in the household suffers from allergies or asthma, because dust mites can't reproduce when the relative humidity stays below 50%. But when you have a home that's very high energy efficiency, that reduces the cooling load and the heating load in terms of temperature, good insulation, good windows, air tightness, you won't need as much cooling anymore. But the humidity load, which they call the latent load, remains the same. It doesn't make it higher, it just remains the same as it would be in any other inefficient house. So it can get to a point where the air conditioning system, which is the way we normally dehumidify, it may not provide enough humidity control with just a correctly sized air conditioning system. So there could be a need for some supplemental dehumidification, particularly in the shoulder seasons in spring and fall, where you really don't need air conditioning. So how was that done in these homes? Well, there were various options. One way is to have a high efficiency Energy Star whole house dehumidifier that is tied into the entire heating and cooling and ductwork system, where it draws air from the interior or from both the interior and the exterior, removes the moisture, and then it supplies low humidity air into the supplied ductwork. There's a humidistat in the living space that makes it come on only when needed, only when the relative humidity rises above your set point. Very similar to the thermostat. Another less expensive option could be to just plan in a location where you can have a standard capacity or portable type, inexpensive but still Energy Star rated dehumidifier. It could be located under the HVAC closet, but separate, not in the return system. Be sure to plan for a drain line and electrical supply, and a place where they can be the built-in humidistat. Again, more duct sealing occurred, especially where the boot connect and the registers meet the drywall. Every point in the system needs to be sealed tightly to prevent unwanted leakage. Energy Star appliances and lighting were selected throughout, mostly fluorescent lighting, use of compact fluorescents, and using that Energy Guide label to help select the most efficient equipment within the budget. And of course, homeowner education was a part of it and needs to be a part of every high-performance home. What were some of the lessons learned through the process of building these prototypes? There were learning curves, and essentially structural versus non-structural framing is a challenge, particularly in a high wind zone, and that needs to be figured out from the beginning. Duct sealing was not the norm in the area at the time, really high performance duct sealing, so some training is needed for that. The air sealing of the foam board below the floor joists was a difficult process. It takes good workmanship and in kind of an awkward position, and so that needed to be redone by the professional after, we found that it wasn't quite up to par. Mechanical equipment was located under the stairs, and that proved to be problematic because it was a tight fit. And so in a future design, having it within the unvented attic would be an easier solution to that. There were some complications in terms of window installation when you have the rigid foam insulation all to the outside. That required figuring out how to handle the detailing of the trim and the siding because of the added thickness of the system. Particularly in terms of a wind zone, the windows still need to be installed on the framing, and then the trim needed to come further out. Transfer grills are important to be able to close doors within a home and have the air distribution still flow freely from room to room, from the supply back to the return. In a place like New Orleans with a lot of destruction, a lot of abandoned homes, security was an issue in these particular projects. Some materials were stolen. More lessons learned. The trades were not accustomed to having to attach cladding through furring strips, and so that took a little getting used to. The treated materials that we wanted to use for that third line of defense against the Formosan termite were not off the shelf readily available and had to be special ordered. Duct sealing to the level that is recommended was not the normal practice, and some training needed to occur there. The porch design with the tongue and groove versus sort of an open, drainable decking was a challenge because the homeowners really wanted something that was closer together. The high wind connectors were a new system for the workers, and getting everything properly installed where every connector is installed the way it was supposed to be at the place it's supposed to be takes supervision and coordination. Window installation posed some challenges because of the added thickness of the insulation to the exterior, so there was training involved there. The truss design was a little bit different from what they were used to as well. The normal mode of construction in this part of the country is just using rafters. And finally, the sequencing of the construction steps was a bumpy challenge. When you do things differently, it can call for different procedures from what the contractor's used to. So that is something that is helpful to plan ahead and to think through in advance. As we shape our homes, we truly are shaping our future. There are some great sources of a lot more information, from general information to technical details to research reports. These websites are readily available with a great deal of free help. BuildingAmerica.gov has a number of publications, building guides designed for each specific climate zone, as well as the new Solution Center database with tons of information, logically organized to make it easy for you to find what you need. BuildingScience.com is a repository of many articles and schematics and designs and case studies as well. Flash.org and DisasterSafety.org are organizations that are dedicated to hazard-resistant home building and improvement, and they have a wealth of information. DisasterSafety.org is also the source of the Fortified for Safer Living Building Guide. LSUAgCenter.com/LaHouse is the LaHouse Resource Center website, where you can find information about the facility itself, but also the My House, My Home pages includes about 80 to 100 articles on all of these topics to help a homeowner plan and design their new home or to make high-performance home improvement. The site also has a free online video library with hurricane-resistant demonstrations on it, as well as building science videos. There is also an online training center with several video-based interactive courses that could apply towards CEUs for professionals. One of the courses is wind-resistant construction practices. And LaHouse Resource Center itself is a real demonstration on the LSU campus in Baton Rouge, Louisiana. It was built to be a permanent showcase of solutions and includes 4 high-performance building systems, 4 different foundation systems, 3 of them raised, 10 different types of windows and doors, 3 HVAC systems, 5 different types of attic treatments, including the unvented attic, 5 different moisture management systems, and it demonstrates the criteria and the guidelines of Fortified for Safer Living, as well as energy efficiency, healthy home, green building programs, and even concepts of universal design for all ages and stages of life. It is possible and practical to have truly resilient homes, even wash and wear houses. Thanks for listening.